Radar MASINT is one of the subdisciplines of measurement and signature intelligence and refers to intelligence-gathering activities that bring together disparate elements that do not fit within the definitions of signals intelligence, imagery intelligence, or human intelligence. According to the United States Department of Defense, MASINT is technically derived intelligence that, when collected, processed, and analyzed by dedicated MASINT systems, results in intelligence that detects, tracks, identifies, or describes the distinctive characteristics target sources. In the U.S., MASINT was recognized as a formal intelligence discipline in 1986. As with many branches of MASINT, specific techniques may overlap with the 6 major conceptual disciplines of MASINT defined by the Center for MASINT Studies and Research, which divides MASINT into electro-optical, nuclear, geophysical, radar, materials, and radio frequency disciplines. Radar MASINT is complementary to SIGINT, while the ELINT subdiscipline of SIGINT analyzes the structure of radar directed on a target. Radar MASINT is concerned with using specialized radar techniques that measure characteristics of targets. Another MASINT subdiscipline, radio frequency MASINT. Specialized MASINT radar techniques include line-of-sight, over-the-horizon, synthetic aperture radar, inverse synthetic aperture radar and multistatic. It involves the active or passive collection of energy reflected from a target or object by loss, static, or over-the-horizon radar systems. RADINT collection provides information on radar cross-sections, tracking, precise spatial measurements of components, motion and radar reflectance, and absorption characteristics for dynamic targets and objectives. Radar MASINT can be active with the MASINT platform both transmitting and receiving. In multistatic applications, there is physical separation among 2 or more receivers and transmitters. MASINT can also passively receive signals reflected from an enemy beam. As with many intelligence disciplines, it can be a challenge to integrate the technologies into the active services, so they can be used by warfighters. Still, radar has characteristics especially appropriate for MASINT. While there are radars that can produce images, radar pictures are generally not as sharp as those taken by optical sensors. But radar is largely independent of day or night, cloud or sun. Radar can penetrate many materials, such as wooden buildings. Improving the resolution of an imaging radar requires that the antenna size is many times that of the radar wavelength. Wavelength is inversely proportional to frequency, so increasing the radar frequency can improve resolution. It can be difficult to generate high power at the higher frequencies, or problems such as attenuation by water in the atmosphere limit performance. In general, for a fixed sensor, electro-optical sensors, in UV, visual, or infrared spectra, will outperform imaging radar. SAR-Ns are a means of combining multiple radar samples, taken over time, to create the effect of a much larger antenna, far larger than would physically be possible for a given radar frequency. As SAR-Ns develop better resolution, there can be an argument if they still are MASINT sensors, or if they create images sufficiently sharp that they properly are IMINT sensors. Radar can also merge with other sensors to give even more information, such as #moving target indicator. Radar generally must acquire its images from an angle, which often means that it can look into the sides of buildings, producing a movie-like record over time, and being able to form 3-dimensional views over time. Line-of-sight radar MASINT. Counter-artillery radar. See article. Counter-battery radar. 3 U.S. radar systems exist for detecting hostile artillery fire and backtracking to its source. serving the dual requirements of warning of incoming fires and counter-attacking the firer. While they are intended to be used in 3 tiers against artillery of different ranges, there can be a problem of having a threat of an unexpected type fired into an area covered by the wrong tier. Proper site selection and preparation is necessary for all types. Proper planning includes avoiding clutter sources such as land surfaces, vegetation, buildings, complex terrain, aircraft and particulate matter kicked up by wind or aircraft. The enemy may attempt to avoid the directional radar systems or even use electronic countermeasures, so active patrolling and activating the radar at random times and in random directions will act as a countermeasure. Complementary acoustic and electro-optical systems can compensate for the lack of omnidirectional coverage by the TPQ-36 and TPQ-37. To complement the counter-artillery radars, additional MASINT sensors include acoustic and electro-optical systems. A variety of ground-to-ground radars serving counter-battery and surveillance roles, and also have some capability to detect helicopters. The LCMR, TPQ-36, and TPQ-37 radars are ideally used in a layered detection system, for short, medium, and long-range detection. LCMR is omnidirectional, but the other two are directional and need cueing from omnidirectional sensors such as the combined electro-optical and acoustic rocket launch spotter or a pure acoustic system such as HALO or UTAMS and TPQ-36 and -37 counter-artillery radars. These 1980 vintage systems are not man-portable and directional, but they do have longer range than the LCMR. Physically heavier than the LCMR, the TPQ-36 Firefinder radar can detect cannon, rockets, and mortars within its range. Artillery, 14,500 meters. Mortars, 18,000 meters. Rockets, 24,000 meters. It has a moving rather than omnidirectional antenna. Current improvements are intended to replace its old control computer with a laptop, enhance performance in high-clutter environments, and increase the probability of detecting certain rockets. First intended to provide a third tier against long-range threats. The TPQ-37 Firefinder radar basic software filters out all other radar tracks with signatures of lesser-ranged threats. New software, required by the mortar threat in the Balkans, allows it to duplicate the Q-36 mortar detection range of 18 kilometers, while still detecting longer-range threats. Proper crew training should compensate for the reduced clutter rejection caused by accepting mortar signatures. Standard TPQ-36 37th radars are semi-manual in the plotting. An Israeli enhancement makes the plotting fully digital. Ground surveillance radar portable, and intended for tactical use, is the man-portable surveillance and target acquisition radar. Originally developed for British use in artillery spotting, as the primary users of MSTAR, like its predecessor, were in artillery observation parties, although it may be used for ground reconnaissance and surveillance. The MSTAR entered UK service in early 1991, slightly accelerated for use in the Gulf War. Its official UK designation is Radar GS number 22. MSTAR was developed and produced in UK in the mid-1980s by Thornemy Electronics. It is a Doppler radar operating in the J-band, and is capable of detecting, recognizing and tracking helicopters, slow-moving fixed-wing aircraft, tracked and wheeled vehicles and troops, as well as observing and adjusting the fall of shot. The US uses it used as PPS-5B and 5C ground surveillance radar sets, and Australia calls its version AMSTAR. The GSR is a ground-to-ground surveillance radar set for use by units such as infantry and tank battalions, and BCTRSTA units. It can detect and locate moving personnel at ranges of 6 km and vehicles at ranges of 10 km, day or night under virtually all weather conditions. The radar has a maximum display range of 10,000 meters and the radar can alert the operator both orally and visually. The APS-PPS-15 is a lighter, shorter-ranged version intended for airborne, light infantry, and special operations force use. These radars are more MASINT than general-purpose radar, as the simpler ones have very little imaging power, but perhaps a light or sound indicating the direction and range of the threat. Recognizing the threat of ground surveillance radar, the Australian military is exploring personal radar warning receivers, approximately the size of a credit card, and intended principally for special operations forces who have to evade ground surveillance radar. Fixed or semi-mobile ground installations. The Cobra Dane ground station radar is an FPS 108. A phased array L-band antenna containing 15,360 radiating elements occupying 95% of the roughly 100 by 100 foot area of one face of the building housing the system. The antenna is oriented towards the west, monitoring the northern Pacific missile test areas. Methods continue to evolve. Cobra duty was intended to gather information on long-range missiles, in a strategic role. One developmental system, Cobra Gemini, is intended to complement Cobra duty. It can be used for observing long-range missiles, but is also appropriate for theater-level weapons, which may be addressed in regional arms limitation agreements, such as the Missile Technology Control Regime, where Cobra duty is built into a ship. This dual-frequency radar is transportable, capable of operating on ships or on land, and optimized for monitoring medium-range ballistic missiles and anti-missile systems. It is air transportable to deal with sudden monitoring contingencies. Cobra duty was supplemented by Cobra Gemini on USNS Invincible starting around 2000 and was replaced by Cobra King in 2014 on USNS Howard O. Lorenzen. Active line-of-sight satellite radar. The Soviet Union used a number of radar-equipped ocean reconnaissance satellites, which used strong radar systems, powered by an onboard nuclear reactor, to visualize vessels. These operated in the push-broom manner, scanning a swath straight down. U.S. radar satellites, however, have emphasized SAR and ESAR, synthetic aperture radar and inverse synthetic aperture radar MASINT. A synthetic aperture radar system exploits the fast movement of an aircraft or satellite, simulating a large antenna by combining samples over time. This simulation is called the synthetic aperture. Coupled with other MASINT and IMINT sensors, SAR can provide a high-resolution, day and night collection capability. Recorded over time, it can be excellent for tracking changes. In addition, when operated at appropriate frequencies, it has ground and water penetrating capability, and is good for picking objects out of deliberate or natural clutter. SAR is not, however, a trivial computational task. As the real antenna moves past the target, the range between target and antenna changes, which must be considered in synthesizing the aperture. In discussing SAR principles, Sandia National Laboratories also notes that, for fine-resolution systems, the range and azimuth processing is coupled, which also greatly increases the computational processing. In spite of the difficulties, SAR has evolved to a size that can fit aboard a UAV. Flying on the MQ-1 Predator, the Northrop Grumman ZPQ-1 tactical endurance synthetic aperture radar started operations in March 1996 over Bosnia. The ZPQ-1 uses a radar signal in the 10 to 20 GHz J-band, and can work in strip map, spot map, and MTI modes. These modes are applicable to a wide range of MASINT sensors. Strip map imaging observes terrain parallel to the flight path or along a specified ground path. Resolution depends on range and swath width, and can vary from 0.3 to 1.0 meters. Compare the two. The radar is not affected by night or weather. Spot map mode covers 800 by 800 meters or 2,400 by 2,400 meters. In MTI mode, moving targets are overlaid on a digital map, as well as large SAR aircraft such as the 8 Joint Surveillance Target Attack Radar System. HUMINT APY-3 radar has multiple modes including ground moving target indication. The US has highly classified radar satellites. Quill, launched in 1964, was the first radar satellite, essentially a prototype. A system originally called Lacrosse Indigo, and finally Onyx appears to be the only U.S. radar satellite system using push-broom scans and spotlighting (SAR). Given that the E-8 is a large aircraft that cannot defend itself, there are U.S. attempts to move the E-8 capability into space under a variety of names, most recently a simple space radar. In an era of budget demands, however, this extremely costly new generation has not been launched. ISAR can produce actual images, but the discipline is generally called MASINT rather than IMINT. A much more modest ISAR capability is on the Navy's SH-60 multi-mission helicopter, carried on destroyers, cruisers, and aircraft carriers. If budgets permit, the proposed E-8 aircraft, the replacement for the P-3 maritime surveillance aircraft, will carry ISAR. P-3 aircraft carry the IN APS-137B5 radar, which has SAR and ISAR capability. This is part of the general upgrading of the P-3 to make it a capable land surveillance platform. The German Armed Forces military SAR-Lupe reconnaissance satellite system has been fully operational since July 22, 2008. SAR interferometry. This technique, first demonstrated in the 1970s from an Army airborne system, has evolved considerably. At first, it estimated the angle of arrival of backscatter power from a pixel on the ground by comparing the phase difference of the backscattered wafers, measured at two different locations. This information, along with the traditional range and azimuth information, allowed one to locate the imaged pixel in 3 dimensions, and hence estimate the elevation of that pixel. Elevation mapping. Interferometric SAR systems have since become an important remote sensing technology, with a very specific height mapping mission. Interferometric SAR systems can now be obtained as commercial off-the-shelf products. Detection of mines, both on the active battlefield and in reconstituting nations with unexploded ordnance, remains a critical problem. As part of the Strategic Environmental Research and Development Program, the Army Research Laboratory, starting in 1997, began an effort to collect, under extremely controlled condition, a library of UXO signatures, BOOM-SAR, to make repeatable measurements. ARL implemented an ultra-wideband low-frequency SAR for validating electromagnetic models and developed target detection algorithms. The instrument is a 20 to 1100 MHz UWB SAR, mounted on a boom that travels at 1 km per hour over a precisely measured range. The SAR is mounted on a 30-ton boom lift platform, such that it can reproduce consistently the depression angles and swath of a representative airborne SAR. Multiple runs can be made with different frequency bands, power levels, resolution, polarization, and motion compensation methods. Basic signatures are recorded over an area of ground that is free of buried metal, but otherwise identical to the UXO test area. Once the ground signatures are complete, runs are made over the test area. Steel crater test area. Once the basic terrain signature is known, signatures are being collected from terrain that has been disturbed in a controlled manner. One such environment is at the Yuma Proving Grounds, a desert area where an existing unexploded ordnance test site, the Steel Crater Test Area, has been used for a variety of sensor calibrations. It contains buried landmines, wires, pipes, vehicles, 55-gallon drums, storage containers and arms caches. For the Army studies to define the signatures of UXO detection, over 600 additional pieces of inert UXO were added to the steel crater test area, including bombs, mortars, artillery shells, 2.75-in rockets, cluster submunitions, and mines. Coherent change detection. In the 1990s, a new SAR application of coherent SAR showed the ability the detection and measurement of very small changes in the Earth's surface. The simplest form of this technology, known as coherent change detection, had obvious military and intelligence applications, and is now a valuable tool for analysts. CCD complements other sensors. Knowing that the surface change may mean that analysts can direct ground-penetrating radar on it, measure thermal signatures to see if something is generating heat under the ground, etc. Compare radar CCD and optical equivalents of the same subject. The CCD would not have been affected by night or weather. Moving target indicator. Moving target indications, at first, might seem just an adjunct to imaging radar, allowing the operator to focus on the moving target. That which makes them peculiarly MASINT, however, is, especially in combination with other sensors and reference material, allows the measurement of a movement signature. For example, a tank and a truck both might be measured at 40 km per hour when on a road. If both turn onto unpaved ground, however, the signature of the truck is that it might slow significantly, or demonstrate much lateral instability. The tracked vehicle, however, might exhibit a signature of not slowing when going off pavement. There are several electronic approaches to MTI. One is a refinement of CCD. Differential interferometric SAR is even more precise than CCD. Its use in measuring the ground motion of earthquakes can complement seismic sensors for detecting concealed underground explosions, or the characteristics of those above ground. Current research and development involves multiple coherent SAR collections to make even more sensitive measurements, with the capability to detect motion as small as 1 mm per year. The new techniques address many of the limiting factors associated with SAR interferometry, such as atmospheric-induced distortions. UHF, VHF SAR. UHF and VHF SAR have begun limited operations on Army RC-12 aircraft and may be implemented on the Global Hawk. DARPA's Watch IT program developed robust low false alarm density change detection software to detect vehicles and smaller targets under foliage, under camouflage and in urban clutter, and developed tomographic imaging to detect and identify targets that have not relocated. VHF, UHF SAR for building penetration, urban mapping and performing change detection of objects inside buildings. Terrain characterization technologies were also developed, including the abilities to rapidly generate bald earth terrain height estimates and to classify terrain features from multipass VHF, UHF SAR imagery. In September 2004, DARPA demonstrated real-time onboard change detection and rapid ground station tomographic processing, as well as rapid generation of bald earth digital elevation models using stereo processing.